So I've had the question about how much do you guys have to hand in. I'd like one package per group. Basically, I just need to prove that you did it. I also saw you do it. Check. I think one of the outcomes is perform an experiment, is it not?
Wait, we don't need to...
I think, right? Is it not? Okay. Do an experiment to relate those different things. Okay, so let's use our highly skilled mathematical abilities to figure out what these formulas are. Okay, so, and normally in the past I would have said, don't write everything down, but because you have a sheet now, just follow along, right? Okay, so we're going to take the results of our experiment and derive some formulas that relate centripetal force Fc to various aspects or quantities of UCM. So when you graph period squared versus Fc, your graph should have looked like this.
Oh.
Did your graph sort of look kind of like that?
I think so.
Yeah, it did.
Sort of kind of?
Yes.
Okay.
It didn't work.
So this tells us, this suggests that it may be an inverse or an inverse squared relationship. Right? Because this is the classic inverse look. So to confirm it, we're going to graph 1 versus a t squared versus 1 over fc. Now, we probably should graph t versus 1 over fc and t squared versus 1 over fc, but I happen to know the answer. It's the t squared one. Right? This is how they used to figure out whether the relationships were what they were. They would make a guess, they would do this transformation, and then they would see if it's linear or not. Okay? So we're thinking either inverse or inverse squared relationship. We're going to do the t squared one because we think it's inverse squared. And when you did that, did you get a straight line? Ish.
Sort of.
Sort of, kind of. Usually we get reasonable results. And I haven't seen a whole lot of groups, but over my many years, I've seen a lot, and they tend to be pretty decent.
That was a fun lab.
Was it? It is a good one. This is the kind of lab that I remember doing in university, except they would expect you to do it all in one sitting. And you wouldn't leave until you're done.
Why does it like didn't finish? Actually,
You wouldn't leave until you're done.
What if there's a next class?
You wouldn't leave until you're done. There is no what if.
Were
That you get a 0 on the lab. Did I tell you my little secret about finishing labs quicker?
do everything beforehand.
Exactly. Find out someone who's taken the class before, because they use the lab over and over again, right? You can do all the prep work ahead of time, right? You can get the table made. Back then we didn't have computers, so we were doing all the graphs by hand. So we knew what the graphs would look like ahead of time. So we'd have like the axes all done and labeled, everything perfect. All we had to do was stick our data in. We were in and out of that lab in an hour, every single time. And every other group was like, how do you guys finish so early? Well, because it's Thursday afternoon, it's 4 o'clock, we don't want to be here any longer. We did all the work the previous Sunday in the afternoon. We're in and out of there in no time.
Good plan.
I'm going to use that.
One of the best things I ever learned there, yeah. Okay, so this suggests that because we get a straight line graph here, this suggests that t squared is that funny looking symbol, 1 over fc. And what is the funny looking symbol, Johnny? What does the funny looking symbol mean?
Half a...
Don't know. It means proportional to. Johnny, have you figured out that you're supposed to fill stuff in here?
Oh.
Yeah, you're supposed to fill stuff in. That means it's proportional to. So t squared, the value of the period squared, is proportional to 1 over fc. So in English, Mr. Ben, when the centripetal force was bigger, when you had more more washers on, that's a greater centripetal force, what happened to the rubber stopper? Did it go? It spin faster, right? So that would mean if it spins faster, that would mean that the period would be shorter, right?
Yes.
Spinning faster, period smaller. So, bit more washers means less period, which is why it's a inverse relationship, right? As one goes up, the other goes down. Does that make sense, Tarn? But it just so happens that it's t squared, not just t. If you graph t versus 1 over fc, you would get a parabola. That's why we graph t squared. Okay? Everybody with me so far? All I'm doing is now identifying the types of relationships, and then we're going to put it all together. It's going to be like a beautiful souffle of stuff. No, it's not going to be a souffle at all.
Sure.
It's going to be a formula. Okay, what about period squared versus radius? What did you find? As you increased the length of the string and made it longer, what did that do to the speed?
Slow it down.
Slowed it down. And remember, slowing it down means the period actually gets longer. So in other words, the bigger the radius, the bigger or smaller the period? Bigger. And so you should have gotten a graph like that. And again, if we graph period versus radius, you would have got a parabola, and you would have went, oh, I know, I got to make that period squared, and that's when you get the straight line. I'm kind of speeding things up for you a little bit. Sure, sorry. No, they're over there.
Oh.
Here we go. Yeah. So this implies that t squared is proportional to r. The bigger the radius, the bigger the period squared. Okay, now the last relationship. What did you find, Josh, when you increase the number of rubber stoppers? So bigger the mass on the end, what did that do to the speed? Slowed it down. So the more if it's slowing it down, that means the period
Gets longer.
bigger, right? Slow speed means high period. So bigger mass, bigger period, so that means it's what kind of relationship? Inverse or direct? Direct, right? So you should have got a reasonably straight line. Usually this is the one that we get the worst results, and that's because you're using a different swinging thing every time. And you can't keep that string length constant, right? But generally we only got 4 too, right? So that's the other reason. 4, you only get 4 data points. Okay, so this implies that t squared is proportional to m. Right? The bigger the mass, the bigger the period squared. Okay. Now, can I combine all 3 of those proportionality statements? Of course we can. Of course we can. Which is exactly what I'm going to do.
And it is a constant of proportionality.
So we're going to combine our proportionalities together, and we get t squared is proportional to rm over fc. Okay.
Is what?
T squared is proportional to r times m over fc. Now the reason that we do this is because we're going to take this relationship that you've discovered through your experiment with my guidance, of course, and we're going to create a series of formulas that we can solve problems with.
Where's the proportional button?
It's not an equal sign yet. It's just a proportionality. That's all it is. Okay? The next step is, how do you turn, and I don't think I've taught this yet. I used to teach it many moons ago in grade 12. How do you turn a proportionality into an equation? Do you know? I don't think this is ever taught the kids. It should be. Do you know the relationship between circumference and diameter of a circle?
Yeah, it's pi.
Not the number, right? But the relationship is the bigger the displacement, or the bigger the diameter, the bigger the circumference. C is proportional to D. C is proportional to D, right? But there has to be some number between those. When you go C equals pi times D, this number, pi, is the circumference divided by the diameter. This is a constant. It's always 3.1415926, blah, blah, blah.
Can you say any more of it?
What's that? No, I can't. As far as I know. So, t squared is equal to KRM over FC. So what did I do here? I changed the proportionality to an equals, and I inserted the letter K, which is a constant. Of course, we use K. It's called the constant of proportionality. Now, why, Mr. Bennett, do you use a K and not a C? Can you not spell?
I'm just going to put constant. Okay.
You could do that. C is a special constant. Anybody know what it is? It's in the famous equation, E equals mc squared. Yes, just like the rapper, right? Anybody know what? Really, there's a rapper, but his name is...
I don't know.
Oh, MC. Is that what you mean?
Yeah. Is that again?
Like MC Hammer?
Yeah.
Yeah, that was like my day. Hammer time.
Yeah.
Yeah. Wore the big pants. Yeah, no, it's a Einstein thing, right? E equals mc squared.
Yeah.
The C stands for the constant speed of light, 3.0 times 10 to the 8th. So it's special, so they reserve C for it. K is generic constant. Okay, so T squared is equal to KRM over FC. And we're going to rearrange that too, because we really want to know what kind of centripetal force we're talking about. So all I've done here is I've taken the T and the FC and I've swapped them. Okay?
Okay.
So the results of our experiment lead us to believe that there's some magical formula called FC equals KRM over T squared. But to make it work for us, we'd have to figure out what the letter K is. We need a number. Would it be pi? Would it just be pi RM over T squared?
No, or else you would get pi.
No, I wouldn't. I might lead you this far, but do you think pi might be involved? I mean, circles, right? Probably. Okay, so I'm going to do some mathematical wizardry to come up with that. Now, I'm going to be doing some gymnastics, not literally, just mathematically. No, we haven't really got there yet. Okay. I'm going to compare this to our old friend, F equals ma. Right? So F, or FC, which is a centripetal force, is equal to mass times centripetal acceleration. Right? Do you see how these kind of look? Well, we got an F over here. We got an M, right? So if you compare them, right? Like, there's the M. So what does that mean? It means that the AC should be KR over T squared. So we're predicting our formula for centripetal acceleration is KR over T squared. That is our predicted formula, based on experimentation. We still don't have a number for K. Okay? But using some geometry skills and some algebra, we're going to do some, and there will come up.
Do all teachers do this deriving stuff, or are students in other schools like expected to learn this stuff?
I have no idea.
I think it's
You're supposed to do it. I interpret that as do it with me, which I seem to think is pretty fair. I can't imagine too many schools would say, I mean, you certainly couldn't expect to do this without guidance the first time. And then once you've done it like 6 times, what's the point of doing it on your own? Doesn't make sense. Having said this is the kind of thing physics profs do. Is they love doing this kind of stuff, right? So as long as you guys have sort of seen it ahead of time, I don't know why. I kind of like doing it.
They derive it in front of you, and then you just
Well, you just write it down, and they do exactly the same thing. They derive it in front of you, and then you use the formula to solve problems. They do it exactly the same way. I have to admit, I kind of like doing this. It makes me feel good about my mathematical skills. But I also do this like twice a year, right? So, yeah. And I've got my own notes to follow too, so it's pretty easy, really. I will say that this is one of the more challenging derivations, for sure. So we're going to attempt to derive a formula to see if it matches our prediction and see if we can determine a value for k. Okay, so that is our end of experimentation summary. Now we're into the math part. Okay, so I think generally all I did was cut and paste out the formulas, right? You just have to fill in the formulas? Because that was the easiest thing to do. So, in one complete revolution, the distance traveled d is the circumference. When you go all the way around, that distance is the circumference of the circle, right? Okay, do you remember the formula for circumference of a circle? Sure you do. 2 times pi times r, right? Or pi times d, and d is 2r, right? Circumference is 2 times pi times r. And the time is the period. Now, have I told you that we use big letter T for period? You use big letter T for period. So if we were to write speed, speed is velocity, which is distance over time, which would be distance, 2 pi r over time, period, right? Velocity is distance over time, and the distance traveled is the circumference, and the time is the period, and circumference is 2 pi r over t, and so the velocity, v, is equal to 2 pi r over v. So label that saved equation number 1. We're going to come back to it. Sort of put it on the shelf, hang on to it. Okay? Does it say that on your sheet? Saved equation number 1?
Yep.
Put like a number 1 in big bold or something like that, so you can find it in a bit. Sure. Okay. Centripetal acceleration. Given the formula for acceleration, which is a is equal to delta v over delta t. Delta v stands for the change in velocity, right? The time, delta t stands for change in time. So we're going to rearrange that to delta v is equal to a delta t, just a simple formula derivation, or manipulation, I mean. If we're talking about an entire revolution, the delta t, the change in time, is in fact the period, and the delta v is delta v total, or the change of velocity for an entire period. So I've just sort of relabeled things. Okay, and again, remember, you don't need to be able to do this. You just need to sort of be witness to and try to follow along as best you can. So, delta vt, total change in velocity, is equal to a times big T. It was my high school buddy, big T. Saved equation number 2. Okay, now I hesitate to even show you this slide. This slide is, okay, so if you don't get this slide, it's okay. This is kind of an aside. Okay? It's kind of another way to look at this, an aside. Do you guys know what an aside is in drama? Like where there's dialogue and then one of the characters kind of has a little voice to the side that no one else on stage hears, that kind of thing? Yeah, so that's what this is, okay? So if you don't get the slide, it's okay. Another way to think about delta V for whole revolution. Suppose several instantaneous velocities are recorded. These are shown as tangent lines below. So just looking at the circle right now. Okay? Danielle, don't give me that look already. Okay. You're giving me that, I don't know what he's talking about look already. I've barely started. Okay. If I were to find the velocity at those points, we already know that it's the tangent, right? No. Okay? And the longer that v1, the length of this determines how fast it's going, and the direction is the direction, right? So at that point there, it's going that fast in that direction. At that point there, it's going that fast in that direction, and so on. right? Each vector v1, v2, v3 is the same length, even though I didn't draw them very well, as the speed is constant. And the value delta v in red is the difference between v1, v2, and so on. So this red thing here, this is the change in velocity, delta v1. It is the difference between this v2 and that one. If I subtracted those vectors, okay? I subtracted them. Okay, if we place v1, v2, v3, if we took all of those v's, let's say I took 8 of them, and we placed them all tail to tail, I haven't really given you that information, but it is another way to show vector subtraction. So if you place them all tail to tail, it would look like that, right? This would be v1, v2, v3, v4, v5, and so on, right? And you place them all tail to tail, it's another way to show vector subtraction. And this vector here would be delta v1, this would be delta v2, this would be delta v3, and so on. Now that's only with 8 individual velocities taken. Okay, now, does it look kind of circular to you? Sort of, although it's actually 8-sided, right? If there's 8 of these, I think there would be 8 of the red ones, right? But I don't have to take 8. I could take way more than 8. I could take 360. I could take 720. I can take as many as I want. And the more I took, the more circular it would be. So that's kind of a calculus concept to take it to the extreme. So the total change in velocity, delta Vt, total change in velocity would be delta V1 plus delta V2 plus delta V3 plus delta V4. And when you add all those vectors, well, you end up at back at the start, and you more or less have a circle, right? And what would be the radius of this red circle? No, the radius. The radius would be this V1, right? And V1 and V2 and V3 and V3 are all the same. So delta Vt, total change of velocity, is delta V1 plus delta V2 plus blah, blah, blah. And that would be the circumference of the circle, which would be 2 pi r, where the radius of said circle is V1, V2, V3. And so you get delta Vt is equal to 2 pi, not r, but 2 pi v, because the r is replaced with the v.
Imagine going on a highway with a tire like that. What?
And I get that formula, or that whole idea is that I probably should spend more than a minute and a half explaining that. Although I found in an experience, if I spend 10 minutes, you still don't get any more than if I spend a minute and a half. So, moving on. Yeah.
I'll just remember the picture.
Yep, I understand, Cass. Yeah. Don't worry, I'm going to bring it all together and give you a nice, beautiful formula present at the end. No, we're going to combine them together. That's why we've got them saved. Okay, you still with me? Taryn, what time? 3:15? Oh, okay. Okay, let's go back in time. Remember equations 2 and 3. 3 was the one we just did, 2 was the one before that, obviously. They were delta Vt is equal to A times T, as well as delta Vt is equal to 2 pi V. Okay, those were the last two. Now you'll notice that they both are delta Vt's, which means we can
Put them together.
Smoke them together. And you get At is equal to 2 pi V. At is equal to 2 pi V. Not in the box yet.
Oh, shit.
Not in the box yet. Riley. On the recording. We're gonna have to do some video editing, beep that out.
It's not like anyone.
You were gonna say it's not like anyone's gonna listen to that. Christine is watching this somewhere. She's probably got like a little cousin with her. Gonna be watching this, and now she's gonna have to explain what that word is, who you are.
Who I am, yeah.
Oh, she's not gonna
Very
She's
embarrassing.
on vacation, she's not gonna be watching this.
You better be watching it. All right, so I'm going to take that t to the other side. I'm going to divide by t, and I get a equals 2 pi v over big T, and that is special equation number 4. Or sorry, saved equation number 4. No, not yet, because we're going to come back to it. We're going to combine them all together.
We're not all.
Well, yeah, we're just going to remember it. We're going to name it, right, so that we can go back to it. That's all. We're going to put a little star beside, like we're going to come back to it. Okay, so remember, way back, equation number 1. Equation number 1 was t equals 2 pi r over v. Now, do these sort of look like they're maybe kind of a little bit, they got some, something, did you just put gum in my recycling? Fair enough. Yeah, gotcha.
That's definitely not going to play it out.
Well, I'd rather her do that than stick it underneath the table.
Yeah, good call.
T equals 2 pi r over v. So now what can we do here? What is similar? Well, the 2 and the pi, the t, right? I could put, this is equal to t, I could put that in where? Oh, but that's going to be ugly, isn't it? It's going to be like a fraction, isn't it? Oh, yeah? Well, like I said there, we're going to substitute equation 1 into 4 for t, just like that, which gives us, there it is there. Okay, I just rewrote it. I don't know what it looks like on yours.
Looks like a box with an arrow.
Okay, yeah. So I'm taking this formula here, and I'm taking all that box, and I'm putting it in for t right there. Right? Dawson, no glasses today? Just being a rebel, or? Okay, so what's this going to look like? It's going to say A equals 2 pi v all over 2 pi r. Oh, hey, hang on. Could those 2 pi's, could they possibly cancel?
Yeah.
Possibly.
So we don't even need.
Well, just hold on. You don't like it? Don't you want to get rid of things?
Yeah, but it's.
Okay. So, 2 pi v over 2 pi r over v.
No, it's not in the box.
Leave that one over there. So, you get the 2's cancel, the pi's cancel. Oh, okay. Sorry. I was excited.
You can't cancel those yet.
You can't cancel them. I haven't written them down yet.
Oh.
Okay, so we're going to cancel those now. And we're going to end up with v over r over v. And I don't know if you know about how to flip all that stuff, but it's going to be v squared over r. Look at that. That doesn't make any sense? Well, it's going to be v over r over v. How do you divide? You flip and multiply, right? So that's going to be v times v over r, which is v squared over r.
That's exactly what I needed for that last question.
In math?
Yeah.
Oh, yeah?
Exactly that.
For like proof.
Would have gone it if I wouldn't known how to do that. Would have made it real easy.
Stick around, man. I can teach a lot of things. So look at how nice and simple that formula for centrifugal acceleration is.
Holy cow.
Okay? Now keep in mind, yeah, you're right, there's no number there, is there? There is no number there. Keep in mind that that's a formula that we came up with based on, well, we did the math, but we're going to see now how it matches our prediction. Now you could also say, let's go back to this substitution at the top here, right? You could also say that this formula is 2 pi over t. I'm taking this guy here. Oops. I'm taking this guy here, and I'm rewriting it, but I'm pulling that v out front. Like, if I go 2 times pi times v and then divide by t, is that not the same as 2 times pi divided by t and then multiply by v? Right? Like, you can do that, right? Okay, so I'm going to pull the v out over here. And the reason for that is because v, now if you look at this guy here, the v and the t can swap out and you get v equals 2 pi r over t. So that v can be replaced with 2 pi r over t. And now how do you multiply fractions? Not cross multiply. You multiply the tops, you multiply the bottoms. So you get 2 pi times 2 pi r all over t times t, or 4 pi squared r over t squared. 4 pi, I apologize if it doesn't fit in the box on your paper. I do, I apologize.
You apologize.
Like, are those the formulas we derived?
Pardon me?
Are those like two the
Those are the ones, like if you were going to wrap it up and put it under the tree for Christmas, those are the ones.
So that we're
Want to highlight something?
Almost.
we're done with this phase.
Yeah, oh yeah, we're done with the savings.
Oh.
Yeah, we put them together into that. Exactly. We got to do a little bit more. Those two, you now have 2 formulas for centripetal acceleration. Now I will point out, and this is actually key, you guys, a lot of kids mess this one up, okay? And the reason is this, Riley. What is the area of a circle? What's the formula for area of a circle? Pi r squared, right? Everyone knows that. Area of circle, pi r squared. Notice that this is 4 pi squared r. I see it over and over and over, year after year. I see AC equals 4 pi r squared. It's the pi that's squared, not the r. So think about, you know those Delissio pizzas that are square, the frozen ones? Think about the square pi.
Like a square pie?
Okay, everyone but Dawson, think of the square pi.
Like a imperial pie on the food.
I had Saskatoon pie the other night. Wasn't that, did you have Saskatoon pie the other night?
No, I had raisins.
Awesome. Oh no? Sorry, I hear that. Okay, well, V is velocity in meters per second. R is the radius circle. Note that radius must be in meters. Centripetal acceleration is meters per second squared. Period must be in seconds. Okay, a last little bit of wrap up here. Okay, I got to make it smaller here so I can get it all on the screen.
Oh.
What was our predicted formula from our experiment? Go way back in your pages. What was our predicted formula? It was K equals K, A equals K R over T squared. And what did we derive? We just derived A equals 4 pi squared R over T squared. So what, my friends, is the letter K? This lesson is brought to you by the letter K. What is K?
4 pi squared.
4 pi squared. And you were right, pi is involved.
So then that's like the.
That is the constant of proportionality. That's this version of pi in this formula, Tony. It almost sounds like you know that. Okay, one last thing. We're doing awesome for time. Usually this takes me the whole period and I'm exhausted. Actually, I'm about the same because you guys are just writing less, actually, than normal. Yeah, usually I make kids write the whole thing. That's just stupid.
Yeah.
I won't do that again.
Thanks, Mr.
You're welcome. Okay, so given these 2 new formulas, and I think you've probably you've got them blank there, but you don't need to write them down, right? Given these 2 new formulas for A, how do we make a formula for centripetal force out of them? How do we make an FC formula out of it? Well, it's surprisingly easy.
Just switch the letters around.
No. Danielle, what did you say? Exactly. Put that in for A. Right? Since F equals MA, oh, she's following along. That's good. No, I meant like you understand. That's good. Since F equals MA, then FC is equal to MAC. So all you really got to do, it's the same thing as what Danielle's saying, is add the M to the formulas, right? If this is A, to make it F, it's like F equals MA, so you just put a M in front, right? So you've got, just watch this here. Don't write, just watch. So if you got F is equal to, right, you just put M in front, and that turns it into force, right? Let me make that bigger so that it's
Force.
right. So a force, mv squared over r. You're going to use that one lots. Yeah. Well, it's going to be right here in the box. Oh, you weren't given boxes? Oh. Oh, because I got them on orange, that's why. So the same thing on the other one. If you want it as a force, you just put an m in front. And that is the biggest formula you're going to see this year. Centrifugal force is equal to, I'll get to that, Costa. Hang on. I'll get to that. Fc is equal to m4 pi squared r over t squared. Now, Costa's pointed out my worst nightmare, I always forget to do this, is sometimes I foolishly use big R, sometimes I use little r. I can't explain why. They're the same thing.
So it should be.
Sure.
And the big R is
Big R means raised. The one that really matters is big T means period. Little t just means annual time. Okay? Yes, I do apologize for that. It's just a little typo that I've been battling
I
for
like
years
to
and
write
years.
it down, right?
well. How do you know when to choose which one? Like,
It doesn't matter. Yeah, R is R.
So which one do you do?
FC. Like,
Oh, okay, well, if you know the velocity, you're going to use this one. If you know the period, you'd have to use this one. Right? It depends on what you're given in the question.
okay.
Yeah. It seems to me that this one probably gets used a little bit more often, probably like, I don't know, maybe 70%, 65, 75% of the time. It tends to be this one more often.
But you're going to change that, right?
Yeah. But they are interchangeable.
Is that one on the left for if you have velocity?
Well, because you have the V in there, right? Is that the last slide you guys had? Okay. So that wasn't too bad, was it?
Oh, my brain hurts.
See? It does make you feel smart, doesn't it, that you can follow along with that? Oh. Well,
I just love this class.
thanks, Brad.
Yeah, it's a first name. Ha, 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 ha.
I actually had a student say to me, Mr. Bennett, I feel like I've been going in circles.
So you're putting it.
So I put it in there, yeah. I can't remember who it was. I should have put their name. I had a sweater like that once.
Really?
Long gone and way too small. It was the 80s.
That's awesome.
Yeah, is it?
It's awesome where that.
Like, I literally had a sweater almost identical to that. I think it was more blue than green, but other than that, it's... Look at that old computer, too, eh?
We used to have like that.
Did I used to have my hair like that? No, I parted it the other way a little bit. He's sick.